Let's see if this thing works. I'm going to spend a few minutes working on this. There we go. Hey, it's my defense. Thank you, everybody, for coming to my defense. All right, great. My advisor, Jeff, I want to thank him, obviously. Thanks to the committee scattered about the room. Thanks. All right, so first, I want to say this to all the grad students. Fun fact, research can be depressing. And people don't talk about it, but it's true. And I especially get kind of depressed when I'm watching a defense. Hey, don't worry about it, because everybody feels that way, even though they don't talk about it. And I recommend therapy. It's a good thing. Or you can talk to older former grad students like me. For example, I talked to this guy. I'm unsure who that fellow is, but Jake was who I was going to address now. All right, so that aside, let's talk about this. So big picture. Some of you guys, it might be one of your first math talks. Some of you guys, what is this? What is this? It's a mutiny in the ranks already. Off to a rough start. So it might be your first math talk. You think, I don't know what to expect from a math talk. When I go to a math talk, I always like to ask myself 3 questions. What should I expect in this talk? A very important question to ask next is there food afterwards? And then, when can you doze off? Those are the 3 main questions you got to ask yourself in every talk. For me, what to expect is I'm going to do a series of jokes followed by some stalling tactics until I've wasted enough time to call the defense. That's what you can expect. Is there food? Yes, there is. There is food. I and whoever else who wants to go, we're going out to Destination Dogs in New Brunswick. I reserved the 2nd floor, so it's basically unlimited space. If you want to come, you can just go. Destination Dogs. All right, when can you doze off? So here's the picture. It depends what you're interested in. Here's the stuff we're going to talk about. In here, you should pick some things where you say, I'll try not to fall asleep for that one. Pick one of those. Pick one that you're not going to care about. And, stretch yourself and flip a coin for the third. Who knows? First thing that I'm going to talk about is Erdős-Corrado stability. I'll talk about more later. This is mostly included because of the pictures that I have for those slides. That's the main reason I included this. Another one I'm going to talk about is entropy and permutations. I'm going to direct this one mostly at non-experts. The next thing, hypergraph fractional matching. This one will be very brief. And mostly for experts, if anybody. I might skip it. We'll find out. The last one on the list, matrices with large permanents. Also brief. Yes, they are all in fact brief because I don't have time to tell anybody anything. So the main goal is really just for me to enjoy this and have fun. And hopefully you're not too...
I have a question. What does D stand for?
This guy! Something I didn't collaborate on, but it's still very interesting. If time permits, we'll also discuss 34 diet tips to get your body. You will not believe number 12 edition. We'll see if we can cram that one in there. So, Erdős-Corrado, and I want to emphasize the, let's see if this part works, that'd be fun. Nope. Let's see if this works. There it is, the Erdős part of Erdős-Corrado. We'll get to the beach buddy tips if we have time. We will not have time. So a preamble. What do I do? What I do is called probabilistic combinatorics, and what that is it uses probability, ideally in surprising ways, to answer questions about combinatorics. Combinatorics, you'll see some of it today, but what you want to think is stuff that computer scientists care about, things where the answer is 2 or 4, not where the answer is like square root of 7. Counting sorts of questions. Paul Erdős innovated this idea of using probability in this way, and Paul Erdős had a bunch of friends. Very small samples. Some are in this room. 1, 2, hard to say. 1 would be. He published with these guys. These guys in turn published with each other. So now we've got this picture going on of people who have published with other people. Vocab word. This is a graph. If you publish, maybe you get a little arrow next to you, or a line, and you can see stuff like, oh, well, whoever the heck this guy is, and whoever the heck that guy is, shockingly didn't publish together? Does that sound right? Okay. They were on the same floor of the same building? Different things. Okay. This one. And we got some more people. Another shout out to my company, by the way. We got Professor Vu, Professor Capardi, Professor Beck, and this guy. Can anyone recognize this person?
Yes.
is the correct pronunciation. I was going to fish for that for 10 minutes if I had to. These guys publish with more guys, and as he pointed out, yes, this is my advisor, Jeff Kahn. And to throw myself in the picture, we have the high-budget remake of Kahn. So that's a graph. Another shocking independent set, people who didn't publish together. I already mentioned Sachs and Samaretti, but also you throw Beck in there, and now I'm just really scratching my head. How come none of that? Really? I don't get it. But it is what it is. Moving on, so let me say this one real fast. I got some pictures, and if there's one thing I want you to get out of this talk, it's the formatting. But I spent a while doing that. And by golly, I want you to say, this is a nice picture. Yes, it is. It also took me a while to look that up. Anyway, speaking of formatting, there's authors on this one. We have me, Pet Devlin, because 2 weeks ago...
Can you get the chalkboard light and turn it off?
2 or 3 weeks ago, there was a discrete math seminar speaker. Is that better?
Yes.
Okay, great. Discrete math seminar speaker, and he referred to this paper, but he called me Pet Devlin, which I thought was an accident until I thought about it longer and realized that my cat did, in fact, contribute a lot to that paper. And we also have Jeff Gaines. Now I'm going to pretend that there's any content to this talk. Kineser graph, what's that? We'll need this. So nodes, in the graph I showed you a bit ago, the nodes were people. Here the nodes are going to be k-element subsets of 1 through n. Here's some 2-element subsets of the set 1 through 5. Alright, there they are, dots. And we're going to connect 2 dots if they have absolutely nothing in common. It's hard to say if you can see this, but for example, this one says 3, 4, this one says 2, 5. They have nothing in common. We're going to connect those, and we're going to connect all the things that have nothing in common. You get a pretty picture. It's the Peterson graph. Okay, great. And then you can ask questions about graphs like you usually do. What's the largest collection of nodes in this picture that contains no edges? Here's one. We got 3 nodes here, doing pretty good. No edges between those 3. Can we do better? Can we get more than 3? Yeah, this one works.
Ooh.
Thanks, Jacob. You wait for the next slide. Here's 4 nodes that have nothing to do with each other. Turns out this is the best you can do in this graph. And the Erdős-Corrado theorem is a statement about the largest independent sets in this Kineser graph. And it's precisely this thing, that if you have too many nodes, you have to have an edge. And too many is quantified, and also so are quantified the sets that have the maximal independent sets. So there's our Erdős-Corrado. And then Volovash asks, what if we take this classical, old, important result, and we take the classical result and we add random noise to it? Is the result still true? And the answer is going to be like, well, I don't know, there's some randomness involved, so we can't definitively say yes or no. But the question is it probably still true? So if we say, take this picture, and we're going to just, for each edge, we're going to flip a coin and throw it away. And we're going to throw it away, keep it with probability P. So maybe we flip our coins, and the edges that remain, boom, maybe that. That's a new one, and that took a while. And then you say, well, if this is the coin flips that happened, is the result still true? Namely, you can't have too many vertices that have no edges between them. Well, if these are the coin flips, then no, it's not still true. We could add this guy, for example, and this would be randomness that results in the thing not being true anymore. So the question is, what sorts of randomness, what degree of randomness can this theorem withhold and still be true? Let's get our feet wet. If P is 1, so we're keeping each edge with probability 1, then the thing is completely unchanged. We've kept everything deterministically with probability 1, so the result is still definitely still true because we didn't change anything. We've added no noise. If we go further, P is 0, then we're keeping each edge with probability 0, all the edges will disappear, and then the thing's not even close to true, the whole thing has no edges, so it's definitely false. And the whole question is, what happens in between? You want to imagine P is some sort of knob that you get to play with, and on the one end of the spectrum, if it's all the way up, cranked up at 1 or whatever, and there's no noise, then the thing's true. If it's cranked all the way to the other end and there's a lot of noise, it's definitely false. And where in between does it transition between true and false? That's the question, and Jeff and I ended up solving this one. D, again, is this guy. We found exactly what the where it transitions, the threshold between being almost definitely true until you get about here. Once you blow past whatever this thing is, it switches to almost definitely false. And we have something else in the very most extreme case where you have...
And by true, you mean the bound is exact n-1, true state -1. Or
Yes,
symptomatically true or something.
Yeah, more precisely, the maximal independent sets are exactly the same as they were before. The independence number didn't change, and you didn't get any new maximal independent sets. So the full Erdős-Corrado with equality of phenomena is still true, and we found the threshold for that up to a multiplicative constant. You can zone out. Now I'm going to talk to people who are like more in the know. And these numbers come from the main obstruction here of why you would expect this Erdős-Corrado theorem to fail. It's precisely because of something like this, where you had a really big independent set to start with, and then you, for almost free, get to throw in this extra guy in a cheap way. That's the obvious obstruction, which is easy to figure out the threshold. And in fact, yes, up to at least order of magnitude, that's right. In the most extreme case, where we have the sets are almost half the size of the universe, that obstruction tells you it should be 3/4, and we prove something like 0.99 bunch of nines. So the truth is somewhere in there, which ain't bad. Some folks call that the interesting part of the problem. But if you make it think
Extremely close to 1, it can break down.
if you make it equal to 1, it's still definitely true, and it switches between true and false somewhere that's not technically 1. Which ain't bad, because what we're aiming for is something that's also a constant.
Okay.
But it doesn't make sense to put it in this form of saying it's within a constant of the truth, because the truth is a constant. Okay. Anyway, I'm gonna move on. There's a pretty picture in there. Some randomness. Cool, great. Let's talk about something else. Entropy and permutations. So this one, we got 3 objects. We have me, rather alphabetically, Hussein, feeding like a baby kangaroo. How adorable is that? We have me, the pirate with a cat on my shoulder, pretty adorable. And then we have my advisor, Jeff Shere Khan, about to maul a poor orphan boy. All right. So you ask yourself, entropy and permutations, but geez, Pat, what is entropy? This is the one that's mostly for non-experts, so like this would be a good dose if you heard this talk recently. Sorry. What is entropy, you ask? And here's a terrible answer that won't help you. There it is. But what I want you to think about entropy is as a game, like Guess Who. So the way it works, I randomly pick something. If you've never played this game, it's not that good. I didn't really mean to doze off.
Well, apologies if I take you literally.
I'm surprised you listen to me at all. Pat randomly picked something, and the other guy, he asks yes/no questions to try to figure out what I picked. And the entropy is almost literally the number of questions you have to ask to figure out what I picked. The almost literally part is that there's some probability, expectation sort of a thing involved and limits. But other than that, it's dang close. So the way that I randomly pick something, that random process might be easy to guess because you say, well, Pat always picks Sam. So I don't have to ask any questions. He picks Sam. That'd be a bad way for me to randomly pick. Or maybe I randomly pick something in a different way where you need to ask more questions. And the number of questions you need is the entropy of whatever process I was using, whatever random elements gave me to that outcome. High entropy means high uncertainty. If you're like, oh, there's so much entropy involved in Pat's randomness, you have to ask a lot of questions to figure it out. So when I was a kid playing Guess Who against my brothers, which this guy always made me think it was modeled after that guy. They looked almost the same growing up. They would beat me for 3 reasons in this game. Reason 1, I didn't ask very good questions. Reason 2,
What kind of questions did you ask?
I don't know, I was like, is it Tom? And they were like, no. I was like, all right. And I like remove one of them. That was a bad question. Reason 1, I asked bad questions. Reason 2, my distribution had very low entropy. I didn't like pick from all the guys. There were like 3, and I was one of those guys basically every time. So if I pick with something with low entropy, they can guess it quickly and they can beat me, which is bad. And reason 3 that they beat me in this game is I bet they cheated. So anyway, entropy. And if we're playing the title game, then maybe you'd ask what a permutation is, but that's even easier. What's a permutation? It's an ordered list of numbers. Like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or, hey, here's another ordered list, 9 through 0. Or 214-867-5309. Fun fact. Dallas area code. Now we know. Very vague question, which was the one we addressed. If Pat picks some sort of random permutation, I pick one of these and I pick it in a random way, but my random process has some sort of noticeable biases. I'll make this more formal on the next slide. Does that mean that the outcome is necessarily going to be somehow more predictable? Will it have low entropy? You say, well, biases, that doesn't make any sense. Tom Layton and Ankur Muitra, they asked more particularly, suppose that for any two numbers like 3 and 4, Pat either noticeably prefers to place 3 before 4, or maybe the other way around. If I were like doing a really random uniform from all the permutations, then you say, which comes first, 3 or 4? I'd say, I don't care, it's a coin flip, 50-50. But no. The way that I'm picking my permutations, you say, what comes first, 3 or 4? And I say, well, there's like a 51% chance that 3 comes first. There's some sort of noticeable preference. In other words, the probability that your one guy comes before the other is never very close to a half. Think always 51% or 49%. Never very close to a half. So if you have a permutation satisfying this for all A and B, does that mean it has low entropy? Yes, in fact. If you have blah, blah, blah permutation where the distance from how likely is it to a half is bigger than epsilon, then the entropy is bounded by something like this, which is something. Its entropy is not as big as it could have been. So, yes, it has low entropy. This condition does make it easier to guess what the permutation is. Cool. There are those things. And you're thinking, but geez, Pat, I want 3 bullets that talk about the proof. Okay. So we used regularity, very weak version. Then we used some sort of combinatorial bookkeeping gadget, and something like coupling. You can argue that it's not there anymore, but it was earlier. And then maybe you ask, well, what's this delta, Pat? How does it depend on epsilon? We prove such and such, but it should really be somewhere down here. Okay. I'll pause real fast for any questions.
Sorry, this is somewhat semi-real question. Do you have an example of a probability distribution where all but one of the pairs, and then the entropy is okay, is not less than 1 minus delta?
No. So this condition is that for all A and B, there's a preference. He wants not for all of them.
Yeah, switch one of them. If you have one that's good for all of them, then reverse that.
Huh? His question was if we somehow relax the condition that this holds for all A and B, you still get this. If it's 1, you can still do like a regularity lemma thing just fine. That won't damage the proof. Swastik asked this question earlier, but if you throw away too many, you can get into some, what do you call it, pathological sort of examples or whatever, but I don't know what the tolerance there is. It's a good question. Well, 1's okay, but not half.
Right.
Yeah.
So shouldn't the entropy increase by at most 1 if you have all but 1?
No. What? What?
No, suppose you have all but 1 pairs satisfy that thing. Shouldn't the entropy be at most this plus 1?
Maybe. Your reasoning being I'll ask about that pair and then I don't buy that because I don't think it works for, well, maybe. That does sound? He likes it. But if we only have half the edges.
No, that is not true.
Yeah, but wouldn't the argument then say something different? Oh no, because then, okay, never mind. Maybe, I don't know. Good question. Sounds reasonable. Other questions?
Can I ask a simple question?
Go for it.
What do you mean by coupling in that context?
So coupling is a very generic term. You know it when you see it, but the general idea is you have some random thing you care about, some random thing you understand, and then you somehow view those in a way where you say, oh, now I can use the thing I understand to realize the thing I care about. Let me give you a quick example, which is almost coupling. Don't yell at me. Let's say we're playing, not a game, but I got a big bucket and it's got numbers and everyone picks out a number and the winner is the one who picks out the number 1. And then I say, would you like to go first to pick your number out of the bucket or would you like to go last? And you're like, I don't know if I want to go first or last. If I go last, then someone probably will win before it gets to me. But on the other hand, if I go last and no one's won by the time it gets to me, I'll definitely win. So so that's the randomness we care about. A randomness we understand might be, let's pretend that I give everyone a ball and I say, don't look at it. No one's allowed to look at it yet. And then I say, if you want, you can switch with the guy who came in last. You can switch your ball with his ball. And you're like, why would I do that? No one's even looked at these things yet. And there we can understand that everyone has the same chance of getting this special ball. And if you couple this and say, okay, well, so step one, give everybody a ball, tell them not to look at it. Then we reveal them, Cole, what did you get, Jen, and so on. You can see how the thing we understand connects to the thing we didn't understand. That's a basic example of coupling. Don't yell at me. Thanks. Okay. Okay. Hey, let's move on. We're not going to talk about this very much at all. But I did prepare a lot of slides in the last one, which I do want to talk about. So we got me and Jeff, who's the co-authors on this one. I don't know who's who. This is the dose. If you don't know what a perfect matching is, it's not for you. But it's fast. Perfect matchings and random graphs. When do those happen? And those happen precisely when you don't have any more isolated vertices. Very much precisely. If you throw in edges one at a time and you say, whoa, no more isolated vertices. Fun fact, you have a perfect matching. Okay, great. So we very much understand when you have no perfect matchings in a random graph. And then you can ask this other sort of model of a random graph. We're not maybe throwing in edges one at a time, and we're not saying we'll flip a coin for every edge, but instead what we'll do is for each node, we'll say, Joel, pick 2 people in this room that you're going to be connected to. Dr. Z picks 2 people, Jake picks 2 people. Everybody picks 2 people, or K people, and then we just see what happened. You pick your 2 people randomly, and we see what it is. That's another way to make a random graph. The advantage of that model is it doesn't have that many edges, and automatically it has no isolated vertices. Everyone's connected to somebody because of how it's made. Everyone has at least K neighbors. And fun fact, if you let everyone pick 2 people, no matter the size of the room, there's a super good chance that you're going to be able to find a perfect matching as long as you allow everyone to pick 2 people. So we even understand that, and that's why we would want to think about this K-out random model, because it's a way to ask more about a question we already understood. So then you might ask perfect matchings and hypergraphs. And people tried this. And hypergraphs, if you don't know that, it's not really for you, but they're harder by a lot. And in fact, this is hard. We know roughly, the answer is that roughly when it has no isolated vertices, we have the threshold probability. And this was proven by Johansson, Kahn, and Vu. So if you want to learn more, you could talk to them about it. They're in the front row. And
Johansson.
what was it? You asked him instead? All the same, regardless of who did the work, they all won a fancy prize for it. Good job, then. So this question is much harder, and they solved it, and that was a big deal. They didn't solve it as well because that would be crazy hard. But maybe you want to ask, okay, well, what if we did K-out hypergraphs? So Joel doesn't pick 2 people he wants to be with. He picks, I want to be on this team of 3 and that team of 3. And then Dr. Z picks, I want to be on this team of 3 and that team of 3. And everyone picks teams of 3, this team and that team. And you could ask the same question, which is going to be at least as hard as the one above it. And that one was crazy hard. This one's probably really hard. So if you wanted to make it easier, because you want a publication because you're a grad student and you got to pay the bills, maybe you do a fractional relaxation of this problem, which is some way to make questions like this easier, and then you can answer in this fractional sense. Yes. Just like in the graph case where 2 out, they have a perfect matching. In hypergraphs, if you have some function depending on the size of the sets, you get a perfect fractional matching. If you pick, I don't know, let's say 100 teams of size 3. He picks 100, she picks 100, she picks 100. And everybody, we put them together, we'll be able to get whatever this fractional thing is, which is like the thing we want, but a lot easier to find. Cool, I want to be done talking about this, but questions?
What's the growth rate, roughly?
Something real bad, like R to the R-ish. We honestly don't know why 2 wouldn't work. We know that if you have R to the R, it'll work, and 2, for probably doesn't work, but we don't know why it wouldn't work. So that's a little bit embarrassing, you could say. If you cared about the non-fractional version, you do need at least exponentially many things to pick, just by an expected value of how many perfect matchings you would expect. Thanks for the easy question. Up my alley. Any other questions? We're going to move to something else. So if you were like, Pat, I dozed out, that was good. And we're going to move to the next one. All right. So this is matrices with large permanents. This is the last section we got. And I'll talk about this till I decide that I'm done talking. I don't know when that'll be. But this one's fun. This is a result with Ross. And me. And little known fact, these are different people.
It's a different cat.
Same cat.
Same
Different cat. Well, yeah, Ross came over when she was like 4.5 weeks old or something, and this is when...
That's two counts.
This is 2 cats. Nonetheless, 2 cats, and they're still doing fine.
Trickiest part of the thesis.
Those cats are adorable. So we got this paper out, which I like. It's nice. It came out in about a year from now, but they accepted it a bit ago. So I don't know how to count that. Anyway, so we'll talk about this one. It's kind of cool. Okay. So some setup. Matrix, square array of numbers. Think about something you would type in Microsoft Excel, especially if you're typing in numbers. Permanent, it's a thing. It's this thing. It's the determinant without the plus minus 1. So it's like even easier than the determinant. Look out. If you're like, what the heck does that mean? You want to know that this thing is super important, I swear, and super, super hard to work with, I also swear. It's important and difficult. It looks like the determinant, but the determinant's a nice thing that you know 5 formulas for and 3 geometric interpretations of. And this thing, nope. There's no geometric meaning at all. It's outrageously basis dependent. It's a train wreck. It's even computationally difficult to figure out, even if it were 0-1 matrices. It's just super, super hard and super intractable, yet super important. It shows up all the time. So that's it's a thing that people care about. And if you can say anything about it, that's pretty good. On the other hand, norm. How much does your matrix stretch a vector? This is something, it's a number. You give me a matrix, it has a norm. And the norm is super nice and super easy to work with. It's super geometric. It has to do with these singular values. If you're like, I hate this thing and I don't think about analysis or anything, what the norm is imagine you take the unit sphere, hit it with your matrix, so now it becomes some sort of ellipse or degenerate ellipse if it were singular. And the norm is exactly the length of like one of these major axes. It's how much it stretched the thing. If you want, you can just remember, just think it's the biggest eigenvalue, which is true if the eigenvalues work out. Like if it's symmetric, then it literally is just the biggest eigenvalue. Cool, great. Either way, it's super easy computationally, geometrically, algebraically, it's just great. So we got 2 pieces. Ugly, important, difficult thing. Very nice, very pretty, very easy to work with thing. And it'd be cool if there were literally any connection between them. Not us, but some other guy. Yes, there is. Gervitz says, if you have any matrix whatsoever, fun fact, permanent is less than norm to the n. Which is a cool result and a true result. And I'll probably end up showing you a proof because the proof's real short, which is neat. Anyway, so we have some connection between difficult thing is in fact connected to in a special way to this norm here. And if you're able to follow all these words, then you might think, is this inequality type? Yeah, like the identity matrix, or a permutation matrix, or multiply one of those things by a number. That's about it, actually. You could also do like a permutation matrix, but instead of all the 1s, make them plus minus 1s. Or if you're working over C, replace the 1s with something that has the right modulus. But it's basically permutation matrices. We understand exactly when this is equal and the thing's type. Cool. So there's a connection between the difficult, important thing and the easy, also important thing. Here's a connection. But then, Scott Aronson, who you might know from quantum computing stuff. I don't know if anyone's seen this. This is a Saturday morning breakfast cereal. It's called The Talk. I think it was December.